Okay, so you're probably here because you want to really grasp what's happening at the forefront, the cutting edge of tech.
Yeah,
And you want to do it quickly, right? Without getting bogged down in all the technical terms.
that's what we're here for.
And today we're going to be looking at something pretty incredible. How computers are becoming so much better at seeing and making sense of what they're seeing, especially when it comes to identifying objects from way up high, like from a drone's perspective.
It's really mind-blowing how far we've come in a relatively short time. Think about it. We have drones capturing tons of video and images from the sky. It's a deluge of visual information. But to actually use that information effectively, we need computers that can automatically make sense of it, tell us what they're seeing, and do it faster and more accurately than any human could.
Right. I mean, it's not humanly possible to keep up with that volume of data. So we're taking a deep dive today into the advancements in deep neural networks and computer vision, and specifically how the latest research is making this object detection from aerial images even more powerful. And we've got some really cool stuff to look at, including research that explores new techniques and even a custom data set made just for this purpose, spotting vehicles from above for traffic monitoring, which, has huge implications.
It does. And what we really want to understand today is how these new techniques are actually enabling computers to more accurately and efficiently detect cars, trucks, buses in these aerial images and videos. But we'll also talk about the practical side of things, why these improvements are so important in the real world.
Because let's face it, that's where the rubber meets the road, right?
Yeah.
And just to kind of whet your appetite a little bit, one of the key findings we'll be discussing is that incorporating this element of time, how objects move and change between video frames, that has led to a big jump in how accurate these computer systems are. I mean, a significant leap forward.
Yeah. It's one of those things where it seems obvious in retrospect, but actually figuring out how to do it effectively is a whole other story.
Exactly. So before we get ahead of ourselves, maybe we should back up a little bit. And for those who aren't as familiar with this field, can you give us a quick primer on how computers traditionally learn to see objects in images, like when they're just analyzing a single still image?
Sure. So thinking about just still images, that's really the foundation, right? That's where a lot of this work began.
Like if we were to show a computer a single snapshot from a drone's camera, the early approaches focused on that, right? Analyzing just that one picture. And even within that, there were different ways of tackling it. What were the main categories there?
Yeah, so you can broadly break it down into two categories,
Mhm.
two-stage detectors and one-stage detectors, and they each have their pros and cons.
Okay, so two-stage detectors. What's the basic idea behind those?
So think of these as the more meticulous detectives of the object detection world. A classic example is faster RCNN. What they do is they first go through the image and identify regions where there might be an object of interest, like they're proposing these regions.
Kind of like narrowing down the suspects.
Exactly. And then in the second stage, they really focus on those regions and try to figure out exactly what's there and classify it, is it a car, is it a person, that kind of thing. They're known for being very accurate because they take this two-step approach.
So it's a very deliberate process. But that probably comes at a cost, right?
You got it. The downside is that they tend to be a bit slower because of this two-step process. So if you need something that works in real time, like analyzing a live video feed, they might not be the best choice.
Okay, so that makes sense. So then we have the one-stage detectors. How do they approach things differently?
So one-stage detectors, like the YOLO family, which stands for You Only Look Once, are all about speed and efficiency. They basically skip that whole region proposal step and just go straight for the jugular. They look at the image once and try to predict both where the objects are and what they are, all in one go. This makes them much faster, which opens up all sorts of possibilities for applications that need real-time results.
So it's a more streamlined approach. And you mentioned the yellow family. That's been through quite a few iterations, hasn't it?
It has. We've gone from YOLO 2 all the way to YOLO 5, and each new version has built upon the strengths of the previous ones, making them faster, more accurate, and generally easier to use. Some of the key improvements have involved better ways of extracting features from images and handling objects of different sizes, which is super important in this context, where you might have a tiny car in the distance and a larger truck up close.
And in the research we're looking at today, they chose to use YOLO 5 as their starting point, right?
That's right. It seems like they went with YOLO 5 because it strikes a really good balance between accuracy and speed, which, as we've discussed, is kind of the holy grail for real-world applications like traffic monitoring.
Now, all these models we've talked about so far, they rely heavily on what are called convolutional neural networks, or CNNs, Can you give us a quick explanation of what those are and why they're so important for image recognition?
Sure. So, at a basic level, CNNs are a type of neural network that's specifically designed to process images. Think of them as a computer's way of learning to see patterns. They learn to identify the specific features and visual cues that define an object, like the edges, shapes, textures that make up a car.
It's like they're building up a visual vocabulary of what different objects look like.
Exactly. And the cool thing is they can learn these features automatically from the data. You don't have to explicitly program them to recognize, say, a wheel or a windshield.
Right? You just feed them tons of images and they figure it out. But there have been some interesting developments beyond CNNs, right? Like these transformer-based models that have been making waves in the field.
Oh yeah, absolutely. So transformers, which were originally developed for natural language processing, have started to make their way into computer vision. And models like DETR and YOLOs are using them to great effect. The key idea behind transformers is this mechanism called self-attention. It allows the model to understand relationships between different parts of the image, even if those parts are far apart.
Like they can see the forest for the trees, as they say.
Yeah, exactly. It's like they can take in the whole context of the scene, not just isolated features. We're also seeing more hybrid architectures that combine the strengths of CNNs and transformers, which is really exciting.
So that's a great overview of how computers learn to see objects in still images. But what happens when we move from still images to video, especially video captured from a drone that's moving around?
Things get a whole lot more complicated, that's for sure. Video adds this whole other dimension of complexity.
Yeah.
Because now you're not just dealing with a static scene, you're dealing with motion.
It's a much more dynamic environment, right?
And you have all these new challenges that you didn't have with still images, like occlusion, where objects might be partially hidden behind other objects.
Like a car driving behind a tree.
Exactly.
Okay.
And then you have motion blur, where moving objects can appear blurry in the image, making them harder to detect. And then you have changes in lighting conditions from frame to frame, which can throw the models off.
So if you just treated each frame of a video as an individual image, you wouldn't get very reliable results, would you?
No, not at all. You'd miss out on so much crucial information about how objects are moving and interacting with each other.
So what were some of the early attempts to tackle this added complexity of video object detection?
Well, initially, people tried post-processing methods. Basically, you'd apply a regular image detector to each frame of the video individually. And then you'd try to link up the detections across frames to create these object tracks. So you'd know that, oh, that's the same car moving from one frame to the next.
Kind of like connecting the dots.
Yeah, exactly. And techniques like CNMS, TPN, and TCNN all worked in this way. But these post-processing methods have a couple of drawbacks. First, they can be computationally expensive because you're essentially processing the video sequentially. And second, they're not ideal for applications that require real-time feedback because you need to wait until you've analyzed a bunch of frames before you can start making sense of the motion.
So researchers realized they needed models that could directly learn about motion during their training, not just as an afterthought.
Right. That was the next big step.
Yeah.
To develop these end-to-end models that could inherently understand and incorporate information about motion.
And that's where things started to get really interesting. Can you walk us through some of the key techniques that emerged to capture this temporal aspect of video?
Sure. So one approach was to use something called optical flow. This is a technique that estimates the motion of every pixel in the image from one frame to the next. So basically gives you this very detailed map of how everything is moving in the scene. Models like FGFA and DFF used optical flow to incorporate motion information, but it can be quite computationally expensive.
Because you're essentially analyzing the movement of millions of individual pixels, right?
Exactly. So it's a very granular approach. Another direction that people explored was the use of memory modules, like LSTMs, or long short-term memory networks. These are a type of neural network that's really good at remembering sequences of information. So in this context, they can be used to remember what happened in previous frames and use that information to help with object detection in the current frame. There were even specialized versions like convolutional LSTMs that were developed specifically for this kind of task.
So giving the models a way to track the history of objects as they move through the video.
Precisely. And then you had 3D CNNs, which extend the idea of convolutional neural networks into the time dimension.
Yeah.
So instead of processing a single image, they process a stack of consecutive frames, allowing them to learn features that are both spatial and temporal.
So they can see both where things are in each frame and how they're moving across frames.
Right, but 3D CNNs also tend to be computationally intensive because they're processing so much more data.
It seems like there was this constant tension between wanting to incorporate more information about motion to improve accuracy, but also needing to keep things computationally manageable, especially for real-world applications.
Absolutely. That's been one of the big challenges in this field. And so people started looking for more efficient ways to incorporate temporal information. Techniques like the temporal shift module, or TSM, emerged, which achieve similar benefits to 3D CNNs, but with a lower computational cost.
Hmm.
And there's been a lot of work on various spatial temporal consistency modules that try to enforce smoothness and consistency in the object detections across frames.
And all of this gets even more challenging when you're trying to detect very small objects, like in wide area motion imagery or
Oh
WAMing.
yeah, WAMI's a whole other beast.
Hmm.
Imagine you're trying to detect a tiny car from a drone that's flying hundreds of meters above the ground and covering a huge area. It's tough enough to do that in a single image, but when you have a video, those vehicles become even tinier and they're moving across this vast scene.
Like trying to spot an ant crawling across a football field.
Exactly. So people have been using techniques like ClusterNet and even adapting models like YOLO-5 to handle this challenge. But one of the limitations that the research we're discussing points out is that some WAMI approaches need to look into the future to process the current frame, meaning they need to see frames that haven't happened yet to make a decision about what's happening now, which isn't very practical if you need real-time results.
So that brings us to the heart of what we're diving deep into today. This specific research that focuses on improving vehicle detection from UAVs, from drones, by using these spatiotemporal models, but training them on data that's even richer and more informative, data that includes information about motion.
Yeah. The researchers realized that to really make progress in traffic monitoring using drones, you need models that understand the flow of traffic, not just individual snapshots of vehicles. And to do that, they needed a better way to train these models.
And that's where this new dataset, the STVD dataset,
Okay.
comes in. Why was this dataset so important for their research?
It was crucial because existing data sets just weren't cutting it. There were lots of data sets with images of vehicles from above, but they were mostly just individual images, not sequences of frames that showed how vehicles are actually moving over time. And to train a model that can really understand traffic flow, you need that temporal information.
So it's not enough to just know that there's a car in the image. You need to know where it's going, how fast it's moving, and how it's interacting with other vehicles.
Right. So the STVD dataset, which stands for Spatiotemporal Vehicle Detection Dataset, was designed to fill this gap. It's made up of 6,600 annotated sequences of images captured from UAVs in Nicosia, Cyprus. And the key is that it provides the actual trajectories of the vehicles as they move through the scene. It's not just a bunch of random snapshots.
So they were really trying to capture the dynamic nature of traffic, the way vehicles flow through an environment. What kind of environments did they capture? What were the scenes like?
They had a mix of different road environments, including roundabouts, highways, and city streets. And they made sure to include a variety of vehicle types, like cars, trucks, and buses. Because in the real world, you're not going to just have one type of vehicle on the road.
And they even made sure to reflect the real world imbalance in the number of different vehicle types, right? Like there are way more cars on the road than trucks or buses.
Exactly. It's not just a perfectly balanced data set where you have an equal number of every type of vehicle. They wanted to make it as realistic as possible so that the models would be prepared for what they'd encounter in the real world.
Can you talk a little bit about the technical specifications of the data set, like the resolution of the images and the size of the vehicles in the images?
Sure. So the images are all in full HD resolution, which provides a good level of detail for identifying vehicles. And the size of the vehicles in the images varies, depending on their distance from the camera, of course. But generally, they range in size from about 20 by 20 pixels to 150 by 150 pixels.
And they didn't just collect this data haphazardly, right? I imagine there was a lot of thought and care put into how they captured it and how they annotated it.
Oh yeah, they definitely didn't just send a drone up and hope for the best. They used a UAV that was hovering relatively stationary over different road segments at varying altitudes, between 80 and 110 meters. That variation in altitude is important because it adds another layer of complexity for the models to handle.
Because the perspective changes and the size of the vehicles in the images changes.
Right, and they use this clever semi-automated approach to annotate the data. They manually annotated a portion of the data set, and then they use that annotated data to train an initial object detection model. They then used that model to automatically generate bounding boxes for the remaining frames, and then human annotators would review and correct those boxes. And to make extra sure the annotations were accurate, they had a second independent researcher do a verification pass.
That's great. They took all the necessary steps to ensure the quality of the data. Now, once they had this new, rich data set, they needed to figure out how to actually use it to train models that could take advantage of all this temporal information. And they decided to focus on YOLO-5, right? That one-stage detector we talked about earlier.
Yes, and they came up with some really interesting ways to adapt YOLO-5 to process sequences of images instead of just single images. They essentially created three main variations of YOLO-5 that could handle this spatiotemporal data.
Okay, so let's break down this three variations. What was the first approach they tried?
The first one was called the frame pair model. The basic idea is pretty straightforward. Instead of feeding the standard YOLO-5 model, a single three-channel image, red, green, blue, they fed it two consecutive frames from the video. These frames were combined channel-wise, so the input to the model became a six-channel tensor containing information from two moments in time.
So basically, they just doubled the input to the model.
In a way, yes. And they only had to modify the very first layer of the YOLO-5 network to handle this increased number of input channels. The rest of the network stayed pretty much the same.
So it's a pretty simple way to introduce temporal context into the model. What about the second approach? How did that differ?
So the second approach, called the frame pair indifference model, built upon the first approach by adding one more piece of information. They took the two consecutive frames and calculated the difference between them, pixel by pixel, but using the grayscale versions of the images.
So this difference image would highlight the areas where things had changed between the two frames.
Exactly. It basically shows where the motion is happening. And they added this single channel difference image as a seventh input channel to the model. So now the model was seeing not just 2 points in time, but also a representation of what had moved between those points.
Okay, that's really clever. And what was the third spatiotemporal variation they explored?
The third one was called the two-stream model. It's a bit more complex than the first two. It also used the two consecutive frames and their difference image as input. But instead of combining them all into a single input, they split them into two separate streams. One stream processed the pair of frames, and the other stream processed the difference image. Each stream had its own YOLO-5 backbone network. And then the features extracted by these two separate networks were combined later in the model before being passed to the final detection layers.
So giving the model two distinct pathways to analyze the appearance and the motion information separately. Interesting. They also did some experiments with attention mechanisms. Can you explain what those are and why they might be helpful for object detection?
Attention mechanisms are really cool. They're inspired by how our own brains work. When we look at a scene, we don't pay equal attention to everything. We focus on the things that are most important or interesting to us. And attention mechanisms allow neural networks to do something similar. They can learn to weight the importance of different parts of the input data.
So in this case, they could be used to help the models focus on the parts of the images that are most likely to contain vehicles.
Exactly. And the specific attention mechanisms they looked at were SENET, which stands for Squeeze and Excitation Networks, and ECANet, which stands for Efficient Channel Attention Networks. These both work by recalibrating the different channels within the network, kind of like turning the volume up on the channels that are most relevant for detecting vehicles and turning the volume down on the ones that are less relevant.
Okay, so it's like fine-tuning the model's perception. And how did they actually incorporate these attention modules into their model?
They tried a couple of different approaches. One was to add an attention layer at the very end of the backbone network, just before the features get used for detection. And the other was to embed the attention modules within the C3 modules, which are these key building blocks in the YOLO-5 architecture. They called these modified modules C3SE and C3SEA.
So they were really experimenting with different ways to integrate these attention mechanisms into the network. And all of this sounds really promising, but what did the results actually show? Did these spatiotemporal models and attention mechanisms actually lead to better performance?
The short answer is yes, they did. And in some cases, the improvements were pretty dramatic. The frame pair model, that first one we talked about, it showed an 8.81% improvement in mean average precision, or MAP, compared to the standard single-frame YOLO-5.
Wow, that's a significant jump just from adding one extra frame as input.
It is. But it gets even better. The frame pair indifference model, the one that also includes the difference image, that achieved a 13.43% improvement.
Wow, that's huge. So that difference image really made a difference.
It seems so. And the two-stream model, the one with the two separate pathways, that one had the biggest improvement, a whopping 16.22% increase in MAP.
That's amazing. Just by incorporating this temporal information, they were able to significantly boost the accuracy of the model. Were there particular types of vehicles that the models got better at detecting?
Yeah, that's an interesting finding. While all three spatiotemporal models showed improvement across the board, the biggest gains were seen in the detection of trucks and buses, which the single-frame model had more trouble with. And the two-stream model, in particular, came much better at detecting buses. It seems like incorporating the temporal information helps the models to better distinguish between these larger vehicles and makes them more confident in their detections.
Makes sense. So, what about the attention mechanisms? Did those lead to any further improvements?
So the results with the attention mechanisms were a bit more mixed. In some cases, they did lead to a further boost in MAP, like the two-stream model with the C3SE attention modules in its detection head. It saw a noticeable improvement, largely driven by better truck detection accuracy. But for trucks and buses specifically, the impact of the attention mechanisms varied depending on how they were implemented. The researchers speculated that this might be because the attention mechanisms were sometimes causing the model to misclassify trucks as buses, or vice versa.
So, it's not a simple plug and play solution. You have to be careful about how you implement these attention mechanisms.
Yeah, exactly. It highlights the complexity of these models and how subtle changes in architecture can have big impacts on performance. The researchers dug deeper into this by analyzing the confusion matrices, which basically tell you how often the model misclassifies objects. And this analysis revealed that the single-frame YOLO-5 model often struggled to distinguish trucks from the background and sometimes even confuse them with cars or buses. The frame pair indifference model was much better at separating trucks from the background and cars, which suggests that the motion information was really helping. But it did lead to an increase in confusion between trucks and buses.
So, the motion information helps in some ways, but can also create new challenges. What about the qualitative results? Did looking at the actual images and the model's predictions give any additional insights?
Definitely. The visual results really backed up what the numbers were showing. The spatiotemporal models generally did a better job of localizing those less common classes like trucks and buses, and they were more confident in their predictions, especially when things got tricky, like when there were shadows or when vehicles were partially hidden behind other objects. In those situations, the single-frame model often struggled. There were still some instances where the models might mistake a semi-truck trailer for a bus, but some of those attention-enhanced models, particularly those that incorporated attention in the frame pair and difference processing streams, they showed a lot of promise for improving truck recognition. Even if the bounding box wasn't always perfect, the model was at least identifying the right type of vehicle more often.
So, they were on the right track. And of course, in real world applications, speed is just as important as accuracy. What did the researchers find in terms of the processing speed of these different models?
As you might expect, the spatiotemporal models generally took a little bit longer to process each frame compared to the baseline single-frame YOLO-5 model. But the good news is that the increase in processing time wasn't huge, especially for the frame pair and the frame pair indifference models. Those still maintained pretty fast inference speeds. Some of the attention-based models did slow things down a bit more, but the frame pair indifference model, that one seemed to hit a really sweet spot. It gave a big boost in accuracy without sacrificing too much speed.
So, a good balance of performance and efficiency. To wrap things up, what are the key takeaways from this research? What are the big picture implications for the field of aerial vehicle detection?
I think the main takeaway is that incorporating temporal information, the information about motion, is really key for improving the accuracy of detecting vehicles from aerial platforms like drones. And this has huge implications for applications like traffic monitoring, especially in areas where traditional traffic monitoring infrastructure might not be available or feasible. Being able to accurately count vehicles, identify congestion, and even detect accidents in real time from the air, that can really revolutionize how we manage traffic and plan our cities. And the fact that they were able to achieve these accuracy gains without significantly slowing down the processing time, that makes it even more promising for real-world use.
And what about the role of attention mechanisms going forward? It sounds like there's potential there, but maybe it needs a little more fine tuning.
Yeah, I think attention mechanisms have a lot to offer. They can help these models learn even more effectively, especially for those less common vehicle types like trucks and buses. But the mixed results suggest that we need to do more research to figure out how to best implement and train these attention modules so that they don't create new problems like misclassifications.
So there's still more work to be done, but it's exciting to see the progress being made. What are some of the directions that future research in this area could take?
The researchers highlighted a few areas that they think are important. One is to experiment with even larger and more diverse data sets that have a more balanced representation of different vehicle types. Another is to explore using synthetic data to augment the training data, especially for those less common vehicle types. And they also mentioned investigating temporal augmentation techniques, which are ways to create variations in the temporal data without messing up the important time-based relationships. And finally, they emphasized the need for more research on transformer-based models for traffic monitoring from aerial platforms. So it seems like there's a lot of fertile ground for future exploration.
This has been a fascinating deep dive, and I think the key insight for our listeners is that by enabling computers to see not just static images, but sequences of events in time, we can gain a much deeper and more accurate understanding of the world around us. And with these advancements in deep neural networks and computer vision, especially the clever use of temporal information and attention mechanisms, we're getting closer to being able to really make sense of complex dynamic environments like traffic systems.
It's really exciting to think about the possibilities. We could have smarter transportation systems, make more informed decisions about urban planning, and even respond more quickly to traffic incidents. This technology has the potential to fundamentally change how we interact with our transportation infrastructure.
And that leads us to a final thought for our listeners to ponder. What if we were to combine these advanced object detection techniques with real-time traffic control systems? Imagine a system that can not only see and understand traffic patterns, but can also actively adjust traffic signals, reroute vehicles, and optimize traffic flow in real time. What kind of opportunities and challenges might emerge from a system like that? How would it impact your daily commute? How would it shape the future of our cities? It's a question worth thinking about. We've only just scratched the surface today, but hopefully this deep dive has given you a taste of the amazing things that are happening in the world of computer vision and artificial intelligence. Thanks for joining us.